Okay, so this lesson is going to be on midpoint rectangle approximations and trapezoidal approximations. To begin talking about the midpoint approximations, I'm just going to draw like a basic shape and talk about what kind of rectangle we're using here. So, kind of draw a similar to an x squared shape here. And we'll say that the beginning was 0 and the end of it was 1. What you're doing, instead of having it touch on the left or the right hand side, you're going to draw a rectangle that touches in the middle. So in this case at the midpoint, which would be at 1/2. So the height of the rectangle is determined by that x value and your function. So it's going to touch at that middle, but it's still going to have the width that it would have had before. So you would be finding all this area. Now obviously the benefit to something like this is you have a little bit of area that is over what you're aiming for and a little bit where it's missing, and it's almost like that part would fill that in, and it's not exact, but it's a heck of a lot closer than some of the other ones that we've looked at. So it is a useful tool. Okay, so we're going to do a couple of examples with midpoint rectangle approximations. Here we have f of x is x squared plus 2 as our function. We're going to go from x values of 0 to 4, and we're going to make 4 rectangles. I tried to make it fairly easy so you could understand what's going on. Obviously, x squared plus 2 is a parabola that has been moved up 2. So I'm going to say that that's 2 on our y-axis, and kind of sketch that out. And then my x-axis, say this is 0, this is 4, and label that. Now, because we are doing midpoint approximations, I need to find the midpoints. So the first one would be 1/2, the second 3/2, the third 5/2, and the fourth one would be 7/2. And again, I like to use top-heavy fractions because it's just easier to do the math sometimes. Now, because I'm using 4 rectangles between 0 and 4, the width is still going to be 1. The width of each one is still going to be 1. But I'm going to go ahead and draw these hitting at the midpoint, and being that width of 1. So at each midpoint, make a point on your graph, and then draw your rectangle to the left and right sides of that. And hopefully yours stays put since you're using something that's not technology. Mine likes to disappear on occasion. And so when you're finished, it looks something like this. And now we're going to go in and find out what those heights are, because we're still going to do base times height to get our area of a rectangle. And we're going to plug those x values in that were the midpoints so that we can get the correct heights. We're going to plug them into that original function. So if I do 1/2 squared, I'll get 1/4 plus 2. 2 would be 8/4, so that would be 9/4 altogether. And then 3/2 squared would be 9/4, and I'm going to add 2, which would be 8/4, so 9/4 and 8/4 would be 17/4. Then 5/2 squared would be 25/4, plus 8/4 would be 33/4. And then 7/2 squared would be 49/4, plus 8/4 would be 57/4. And then we will just calculate what our midpoint rectangle sum is. The base of all of those is 1, and I can factor it out like a GCF and then just add all the heights. So I'm going to add 9/4, 17/4, 33/4, and 57/4. which is a little bit easier to look at, and that ends up to be a 29. Alright, so now I'm going to do an example, and I'm going to make this one concave down. So 9 minus x squared would be a parabola that has been flipped vertically because of the negative and moved up 9. So this is actually going to cross the y-axis at 9 and the x-axis at 3 if you are to graph it. We are going between 0 and 3, so we're trying to get that area that's trapped here in this quarter circle looking thing, even though it's not exactly that right here. And we're going to do 3 rectangles. So I'm going to mention the 1 and 2 because obviously with this setup each one would be a width of 1. Because we're doing midpoint rectangles, I do need to find those midpoints. So the first one again is 1/2, the second one is 3/2, and the third one is 5/2. And then before I go figuring out all of my outputs, I'm going to draw those rectangles. They touch at the midpoint, and then I draw left and right to make my rectangle. And obviously my drawing's pretty terrible, but you get the idea. And it just disappeared. Okay, so after you have got your rectangles drawn, you're going to figure out what the heights are. So you're going to plug those x values at the midpoints in and determine those y values. So 9 minus 1/2 squared would be 9 minus 1/4. 9 would be 36/4. So if you subtract, you get 35/4. If you plug in 3/2, 3/2 squared is 9/4. So you have 36/4 minus 9/4, so that's 27/4. And then 5/2 squared would be 25/4, so 36/4 minus 25/4, you're going to get 11/4. And then again, you just do your midpoint rectangle sum by adding up all of those areas, so base times height. And again, the base of each one is 1, and then you just add up the heights like you factored out the base. So 35/4 plus 27/4 plus 11/4. And in this case, I end up with 73/4, or you could have a decimal version or a mixed fraction version, just depending on what your answer choices are if it's a multiple choice question. But for your homework, I'm fine with just leaving it like this. Alright, now let's talk about trapezoidal approximations. So this is making trapezoids. So I'm going to do kind of a different graph here and just explain to you what those would look like. And so I'm going to say we have 0, 1, and 2 as our x values. A trapezoid approximation, you just take the two ends. So like if I was going to do 2 rectangles here, I would have an end that would hit at 1 and an end that would hit at 0 and connect them. And then that makes a trapezoid. And so this end at 1, this end at 2, connect it. Here's my trapezoid. Okay. And so obviously in this case it goes a little bit over the line. Sometimes it will be a little bit under the line, but it's really close to that exact area. It's a little bit better than having that large amount over when you do a left or right rectangle. So that was one of the things that they came up with to make the approximations better. As a reminder, you will be doing area of a trapezoid. So your area formula for a trapezoid is 1/2 height, base 1 plus base 2. That was like something you learned in geometry. Because our trapezoids are turned sideways and they're kind of laying down from what you were used to looking at, your height is really the width on the x-axis. And base 1 and base 2 are the y values that you're using. Because, again, your parallel sides are now vertical instead of horizontal. You've turned it from what you're used to looking at in a geometry situation. Okay, so now we're going to look at some examples with the trapezoidal approximation. The first one, we have x cubed plus 1. Again, this is one of your toolbox functions. The x cubed moved up 1, and that side of it, since we're just looking at the first quadrant, it kind of looks like a parabola when we sketch it, but it's a little bit steeper in real life. We're going from 0 to 2 on the x-axis, and we're going to make 4 trapezoids. So we're moved up 1, we know we're hitting the y-axis at 1, and it's a curved shape. And your sketch doesn't have to be perfect because you're going to plug in and find out exactly what the y values are, so it's kind of just to keep your brain in the right place. So again, I'm going from 0 to 2 on my x-axis, but because I'm going to make 4 trapezoids, I'm going to have to put the 1/2 and the 3/2 in so that I would break it up into 4 even parts. And I'm going to go ahead and draw my trapezoids. So I'm going to connect my points and think about that area. And obviously these are going to be a little bit of an overestimate. We talked about over and underestimates in the previous lesson. And we'll hit that again in a second. But this is our thought process. What we need to do now is find all of the y values because those are our base 1s and base 2s. So I'm going to plug each of those x values in, and I'm going to write its little y value out over it like I normally do. So 0 cubed plus 1 would be 1. 1/2 cubed is 1/8 plus 1 would be 8/8. So that would be 9/8. 1 cubed is 1 plus 1 would be 2. 3/2 cubed would be 27/8. 1 again is 8/8, so if I add that I get 35/8. Then 2 cubed is 8 plus 1 is 9. Okay, so once you have all of that labeled, you want to note that now the height of those trapezoids, the width on the x-axis, is now 1/2. So I'm going to think of my height as 1/2. A lot of the problems we've done so far have been a width of 1 or a height of 1. Now it's 1/2. Your trapezoid sum is going to be really big to write out because you're going to have to do 4 trapezoid formulas. I'm going to show you how to condense that, but we're going to start out writing it the long way because this is the first time you've written it in your notes and you need to understand what's going on. So I'm going to focus on that first trapezoid. The formula is 1/2 height, base 1 plus base 2. And again, that height is the 1/2. The bases are the y values. Then I'm going to add my second trapezoid, which is this one here. So 1/2 height, base 1 plus base 2. Then I'm going to add my third one. 1/2 height, base 1 plus base 2. And then my fourth one, 1/2 height, base 1 plus base 2. Now that's a lot to write out, but that's really what you're doing, is finding the area of those 4 trapezoids and adding them together. But to make this shorter for your future problems, notice they all have a 1/2 because that comes from the formula. The height is all the same because they're equally spaced. And then look at the bases. You have 1, 9/8, 9/8, 2, 2, 35/8, 35/8, 9. All of those that are kind of in the middle, so these 3 are part of 2 trapezoids each, so they get used as a first and then as a second base, and so they get used twice. The 1 gets used one time and the 9 gets used one time because they're each only in one trapezoid. So your formula can be written as base 1 plus 2 base 2's, 2 base 3's, 2 base 4's, and then 1 base 5. So you can count the first base one time, the last base one time, and everything in the middle twice. This is a lot shorter way to write this same exact thing. And when you do make this calculation, it'll be 25 over 4. So for future problems, I'm going to always use this shorter way to write it unless they are not evenly spaced. And occasionally you run into a problem where the widths are different and it's been set for you, somehow it's given to you that they are not equally spaced. Okay, so now I want you to try number 4 on your own. Take a minute, pause your video, and try to do the fourth one. You will be using your trapezoid sum again on number 4. Okay, so now you can check your work. This is the same graph we used before, which was the upside down parabola crossing at 9 and 3. We were going from 0 to 3 on the x-axis, and we were going to make 3 rectangles. So that was kind of nice. It made the width be 1. To get your heights, if you plug 1 in, you got 8. If you plug 2 in, you got 5. If you plug 3 in, you get 0. So actually this last piece is a triangle shape. And that happens sometimes, but you still use it like it's a 0 in the trapezoid formula, just to keep everything working the same way. So in your shorthand version, you have 1/2 your height, which is the width again from x to x. So in this case it's 1. My first base was 9. Then I had 8 and 5 in the middle, so they both got multiplied by 2 because they were in 2 trapezoids each. And then the last one, the 0, was only used by that last trapezoid. So this ended up to be 35 over 2, and hopefully you did pretty well with that. Okay, a really classic area problem that they want you to use the trapezoid formula with is where they give you a pond or shape on the green of a golf course or something like that that would be an odd kind of smooth looking shape that would not be a function that you would graph and pass the vertical line test. So let's just draw us a little pond here, and we'll say that the width has been measured at several places evenly across. Here on the ends it's obviously 0, and then we have let's say this measure to be 12, this measure to be 12, this measure to be 13, and this measure to be 14. Even though I haven't drawn that very nicely on the screen, that's kind of what I had on my paper, and it doesn't matter. You're going to get the idea of what we're doing. And let's say that somehow they also told us that the distance between those measurements was 3. And so these will probably have units on them like feet or meters or something. But if you see a picture like this, or they describe a situation like this, they're wanting you to use the trapezoid approximation. The 3 will be your height, and all of these numbers will be your bases. The 0 is your first base, all these in the middle are your middle ones that will get counted twice, and then the last one will be your last base. And it's not always zeros on the end. Sometimes you get some funky things. So mine happens to have zeros, but you may run across one that doesn't. But anyway, they expect you to do a trapezoid sum. So my trapezoid sum would be 1/2 my height, which in this case is the width of 3. Base 1, 2 base 2's, 2 of everything in the middle, and then the last base of 0. And if you plug that in your calculator, you're going to get 153. So again, I just wanted to throw this in because it is kind of with what we're doing, but it doesn't look like your standard problem. Okay, so what you need to know is whether you are an overestimate or an underestimate when you use the midpoint and the trapezoid, because sometimes they are so close to the graph you can't really tell by your sketch. And so here's how you're going to know. If the graph is concave down, then the midpoint is going to be an overestimate and the trapezoid is going to be an underestimate. If the graph is concave up, the midpoint's an overestimate and the trapezoid is an the midpoint is an under and the trapezoid is an overestimate. I do a little bit of a problem in my head with the trapezoid because I can visualize it better, and I just realized that the midpoint is the opposite of that. So for example, if I had a concave down graph that I was thinking about, if I just did one big trapezoid, I think about, would that be over or would that be under? And if I connect it, I can visually see for myself that that's an underestimate. And if I can do that, I realize if I'm doing a midpoint, it would be an over. And the same thing for concave up. Whether I'm doing midpoint or trapezoid, I visually do a trapezoid in my head. And so if I do a trapezoid, like a large one, I realize it would go over if I was connecting them to, and a midpoint would be under if I were doing a midpoint concave up. But I check it in my head thinking about what a big old trapezoid would do, because I can see that better than I can see what's happening with the midpoint in my head. Or you can just memorize this. Okay, the last thing I want to talk about is notation. So in our previous lesson, we were using the rectangles, and I have some pictures here that talk about those things. Here they were doing right-hand sums, and this notation shows that they were using 8 rectangles, and they got this particular area, and then they used 16 and got this particular area, and then they used 128 and got this particular area. And as you notice, the more that you have, the closer it gets to fitting the actual curve. The less wasted space that you have. And we did talk about that in the previous lesson. Same thing with left hand. Obviously using 8 isn't as good as using 16 or 128. The more rectangles that you use, the closer it gets to fitting the actual curve. So I wanted to give you a visual of that. Because what we're getting ready to talk about, you kind of have to think that way. Delta x. Delta, as you know from your science classes, means change. So delta x is the width of your rectangles. And so some of the problems today, we had a width of 1, some had a 1/2. And error decreases as your delta x goes to 0. Because if you look at those visuals, here, this width was much more than this width, and then this was still much more than these. So the smaller your widths get, the less error you have in your area. And so here's some notation that you might see in relationship to that. We have the limit, your exact area would be the limit as your n goes to infinity. So if you n, remember, is the number of rectangles, so as the number of rectangles you had goes to infinity, of a right hand or a left hand sum would get you an exact area. Another way to write this is using a Riemann sum. Delta x, again, being the width between the x values, as those get to 0, so your width is getting smaller and smaller and smaller, you're getting exact area. Or if you're using a Riemann sum and the number of rectangles is becoming more and more and more, getting close to infinity, then you're getting an exact area. I show you these because any of these could be written into a problem and you need to understand what you're looking at. So if you'll focus on this last one here for a minute, because these two are kind of similar anyway. When you do those rectangles, we always did the y value times the base, or the difference in our x's. So really this f of x part is that y value, is the height of those rectangles. The delta x was the width. So it's related to finding the area of those rectangles. The I is 1, the n is however many rectangles you're going to. So this x sub I with the star is talking about whichever rectangle you're on if you're looking at a specific one at a time, because sometimes with Riemann sums you look at a specific one. And so when you take that limit as n goes to infinity of that, that's when you're getting the exact area. So again, I wanted to focus on, notice this and this is basically how you found the height and width when you were doing them by hand. And finally, although you may see these, we are going into integrand, and I put a little note here about what that x sub I is, and I'm not going to focus on that right now. The limit can be written, the limit we were talking about before, any one of those, can be written as the integrand, which is what we're moving into. And so this integrand symbol, this curvy S looking thing over here, means that we're going to get an exact area between A and B. So A would be our starting place and B would be our ending place on the x-axis. The f of x is the function that we're talking about. And then the dx there is part of the notation that you need to write anytime you're writing an integrand. And those come from up here, that f of x sub I and the delta x. In integrand notation, those are translated, although we're not actually computing areas anymore the way we were with the rectangles. But the dx is part of your notation, and it is important. But those two things come from those previous relationships. And that concludes this lesson.